Welcome to In 5 Minutes. In this video clip, we will discuss types of quantization. There are two types of quantization. Number one is uniform quantization. In uniform quantization, throughout the range of the signal from VL to VH, all the levels will be of equal size. In simple words, we say that in uniform quantization, we use constant step size for all the levels from VL to VH. Whereas the second type is called non-uniform quantization. In non-uniform quantization, we don't use the constant step size throughout the range of the amplitude of the signal. The step size of different levels may be different in case of uniform quantization. So we say that it uses different step size for different levels. Now the question is, why do we need non-uniform quantization? For a simple reason that there might be a signal in specific amplitude range. It may happen that signal is changing, but it is taking very small changes. The values by which the signal is changing is very small. In such a case, it becomes very important to have smaller step sizes of the levels that we have in this particular range. Only with smaller step size and smaller width of the level, we will be able to assign more fixed values in this particular region where the signal is changing by small values. On the other hand, it may happen that in certain range of amplitude, signal is changing by a large amount. In such a case, we may assign very small number of levels in this whole range. In other words, we may assign the levels with greater step size. Now, that is simply because the signal is changing by taking very large values. So when we have fixed number of bits, let's say the number of bits is equal to n, in that case we will have fixed number of levels to be used, 2 raised to m or 2 raised to m minus 1. If we use uniform quantization, then we are using the constant width for each and every level. In that case, we are not giving extra attention to the signal values which are changing by small amounts and signal values which are changing by large amount. So to take more information from the region where signal is changing by small values, we should have smaller step size, and in the region where signal is changing by large values, we can have larger step size. And by doing this, we can use the same number of bits and hence same number of levels and can carry out the quantization with the help of reduced quantization error. If we keep the same small step size throughout the amplitude range, then for large changes taking place in the signal, we will also end up using smaller step sizes, and hence the overall number of levels required will be very large, which will increase the number of bits further. So non-uniform quantization helps us to improve the SNR, the signal to quantization noise ratio, in this type of signals in which the signal is changing by small values in some region and some region taking very large values. Now let us discuss uniform quantization and non-uniform quantization in little bit more detail. We will discuss two types of uniform quantizers, which are called mid-trade and mid-rise quantizers, and then we will discuss how non-uniform quantization is achieved. In uniform quantization, the step size remains constant throughout. In non-uniform quantization, the step size changes. So we have to understand how non-uniform quantization can be implemented. So we have two types of input-output characteristics, which represents two types of uniform quantizers that we have. You can see in the first case, x-axis represents the input level, y-axis represents the output level. This is how input-output characteristics of any quantizer will look like. Let us first discuss the mid-trade quantizer, as it is called. You can see the various output levels that we have start from 0 output level. The very first output level is 0 here. That means any input signal level which falls between these 2 points that I'm marking right now will be assigned the value equal to 0. After that, any signal value which falls between these 2 points, which we have marked again, will be assigned the next fixed value, which is represented by this level. Any input signal that falls between this point and the next point here will be assigned this next level. that we can see on the output axis. Similarly, on the negative side also, when the signal falls between this -2 points and this previously defined point, any input signal which falls between this 2 points will be assigned the fixed level represented by this much value. This will obviously correspond to some negative voltage level. Likewise, every input signal value, which is the sampled value, will be assigned some fixed levels, and you can see the levels we have marked using this horizontal lines.